After this video lecture, students will be able to calculate gas law problems using stoichiometry at STP and non-STP conditions. So gas stoichiometry is very much like regular stoichiometry, except in this situation we're going to be utilizing the ideal gas law in order to interconvert between things like pressure, volume, and temperature, and the number of moles of your substance. So PV equals nRT is going to be basically the link between our moles and things like volume, pressure, and temperature. Let's go ahead and let's look at a practice problem. Okay, it says, so what is the volume of CO2 that is produced at 37 degrees C and 1 atm when 5.60 grams of glucose are used up in the reaction? Now, we've been provided a balanced equation, but as usual, if you were not given a balanced equation, you need to write one and make sure that it's balanced and that you've properly written out all of your coefficients and things of that sort. So before we get started with this problem, let's go ahead and let's look at how we know this is going to be a gas stoichiometry problem. Okay, so what they've done is they've asked for the volume, okay, of CO2 while giving us the mass of glucose. Okay, so once again, guys, anytime you see them giving you one substance and asking for a unit of measurement for a different substance, you know stoichiometry is going to be involved. Now, specifically, how do I know gas stoichiometry is involved? Well, the reality of it is they give us a temperature, a pressure value, and they ask us for volume. So obviously, PV equals nRT is going to come into effect in terms of calculating this problem. So the first thing that we're going to do here is we are going to take the grams of what we were given, which is the glucose, and we are going to convert it into moles. Okay? Once we've converted into moles of glucose, we can then use the balanced equation and stoichiometry to go from moles of glucose into moles of CO2. And once we have our moles of CO2, we can use our ideal gas law in order to calculate our volume of CO2. Okay, so let's go ahead and let's do those. Okay, so we start with 5.60 grams, okay, of glucose. I'm just going to write it like that. Okay, and so in order to go from grams to moles of glucose, we're going to divide by our molar mass. Okay, so if we add up all the numbers on the periodic table corresponding to each element and the quantity that's involved, okay, that's going to give us basically the ability to cancel out our grams of glucose, and that's now going to put us into moles of glucose. Okay, now I could, get that answer, don't do any rounding, and then plug it into the next value. But I'm just going to continue with the dimensional analysis setup because it's the most straightforward in my opinion. Okay, so now that we're in moles of glucose, we want to go from moles of glucose into moles of CO2. So we're going to use the mole ratio. So the mole ratio of CO2 to glucose is 6 moles of CO2 for every 1 mole of glucose. Okay. All right, so if I were to go ahead and calculate all of this out, multiply 5.6 times 1 times 6 divided by 180 times 1, okay, that's going to give me 0.187. Okay, and the units that I'm going to have, glucose and glucose cancel, grams of glucose and grams of glucose, moles of glucose and moles of glucose cancel out, and moles of CO2 are what are left over. So I have now used regular stoichiometry to convert between the grams of one substance, which in this case was glucose, into the moles of another substance. And I've done it by obviously stoichiometry, i.e. using the mole ratio and using the common language of the equation, which is the mole. Okay, so now that I have my number of moles of CO2, they want us to tell them how much volume basically that CO2 takes up. So that's when the ideal gas law comes into effect. So PV equals nRT. Okay, so in this case, we are solving for volume. So really, the equation we're going to be plugging into is nRT over P. Okay, so we know each of these variables. Okay, we know our pressure, is equal to 1.00 ATM. Okay, our volume is what we're solving for. Okay, R is my 0.0821, excuse me, liters times ATM per mole Kelvin. Our N value, okay, we just solved for that. It's 0.187 moles of CO2. Okay, and our temperature is going to be equal to 310.15 Kelvin. Okay, so basically I just added my 215.15 to, 273.15 to my 37 degrees C to put it into Kelvin. So now that I have all these numbers, I'm going to go ahead and plug them into the equation. So my volume is going to be equal to 0.187 moles CO2 times my constant 0.0821 liters times ATM per mole Kelvin, okay, times my temperature, which is 310.15 Kelvin. Okay, all of that is going to be divided by my pressure, which is 1.00 ATM. Okay, so plug all of that into your calculator, okay, and what you're going to get is 4.76 liters. Okay, so moles of CO2 cancel. Okay, ATM and ATM cancel, Kelvin and Kelvin cancel, so what's left over is your liters. Okay, so basically in these problems you're going to first take whatever you're given, convert it into moles of the substance that you are looking for, and then once you get into the moles of the substance that you're looking for, you're then going to, give your answer in pressure or volume or temperature or whatever they're asking for. Okay, so here's a problem. It asks, what volume of oxygen gas must be mixed with 3 liters of methane for complete combustion at STP? Okay, so notice, guys, they have given us very few numerical values here, and they haven't given us a balanced equation or anything of that sort. So really, there's a lot of legwork that we have to do beforehand. So methane is CH4. Okay, combustion reactions, therefore, are going to have oxygen gas. Okay, and the products that you get are CO2 and H2O. So once you've written that equation, you want to make sure that you are balanced. So if we look at our CH4, I have 1 carbon on the left, 1 carbon on the right. Okay, 4 hydrogens on the left, 2 on the right. So I'm going to put a 2 in front of the H2O in order to balance out those hydrogens. Okay, so now I have a total of 4 oxygens on the right-hand side, so I'm going to put a 2 in front of my O2 here in order to balance out the total number of oxygens on both sides of the equation. So now that I have a nice balanced equation, I'm now going to look at what I was given. Okay, so first of all, they told us that we have 3 liters of methane. Okay, so we were given a volume measurement of methane right here. Now they want to know what the volume of O2 is that I'm going to need in order to complete the reaction. Okay, so basically to use up all of the 3 liters of methane. Okay, so in this situation, I'm going to go from volume of my CH4, right, into moles of CH4. Okay, which is then going to be used to get into moles of O2. Okay, and then once I get into moles of O2, I'm going to now go to volume of O2. Okay, so what I want you guys to notice here is that the volume of your CH4 to mole of CH4 conversion is going to obviously require some work. So basically we're going to either have to use the ideal gas law, okay, or we can use a nice little trick that will allow us to shorten this. Okay, so in previous lectures, guys, you've seen this 22.4 liters per mole. Okay, all right, so guys, when you're dealing with ideal gases, which is what we assume most gases behave as, and we'll talk about that in more detail later, when we're dealing with ideal gases, the relationship between 1 mole of a gas and the volume is always going to be 22.4 liters per mole. Okay, so if we plug in our values at STP into the PV equals nRT equation, we would get the same numerical value as if we used this conversion factor right here. So, but we're going to take the shortcut route here because of the fact that it's a little bit more complicated in terms of the number of steps that we're going to do. Okay, so if you weren't at STP, if you are not at STP, you cannot use this relationship. Okay, you must be in standard temperature and pressure. Okay, and also if you can't remember what this relationship is, you can always use the PV equals nRT equation. Okay, so let's go ahead and let's do this. Okay, so we were given 3 liters of methane. Okay, and we want to convert into moles of methane. So we're going to use this conversion factor. There are 22.4 liters for every 1 mole of CH4. Okay, so we've done step number 1. We've converted from volume of CH4 into moles of CH4. Okay, now we're going to do step 2 here. We're going to go from moles of CH4 into moles of O2. And this is where your stoichiometry and your mole ratio comes into effect. Okay, so your CH4, there is 1 mole of CH4 for every 2 moles of O2. Okay, so there's 2 moles of O2. Okay, for every 1 mole of CH4. Okay, so if we go ahead and calculate that out and stop the problem here, we would be into moles of O2. Now, I don't really care about moles of O2. I'm wanting to figure out the volume of O2, so that brings us to a 3rd step here. Okay, so if I want to go from moles of O2 into volume of O2, I could use PV equals nRT, or because of the fact that I'm at STP, I can use this nice handy relationship here. Okay, so there are 22.4 liters for every 1 mole of O2. Okay, so if you go ahead and plug this into your calculator, you get 6.00 liters of O2. Okay, liters and liters cancel, moles and moles cancel, moles and moles cancel. Okay, and you're left with those liters of O2. So basically in this approach, guys, as I said, you could have done the conversions in step 1 and step 3 using PV equals nRT, and it would give you the same numerical values.